Hello and welcome to this video about the trapezoidal rule and how to derive it. The trapezoidal rule is a numerical integration scheme for finding the area under a curve by chopping it up into lots of extremely thin trapezoid shapes and adding these up together. It does this by only using the heights of the function and their corresponding coefficients, and the trapezoidal functions themselves never need to be known. In order to derive the coefficients for this rule, we only need to find the coefficients for a single trapezoidal segment, and then, because the interval width only really acts like a scaling factor, then it can be found for a segment when the width is equal to 1. To calculate the area of this segment is very obvious, since its area formula is well known and is calculated here. But it is good to use the other methods to calculate it so as to get used to using these methods and obtain a better understanding of how and why they work, and also then to use these methods to create more accurate numerical integration schemes, such as Simpson's rule and Simpson's 3/8 rule, which are not obvious and are necessary to get much more accurate values for integrals. And so now to start with the first way of deriving the trapezoidal rule, using a general line with coefficients of a0 and a1, which we don't know the value of at all, but need to have in the process of deriving it, and we'll use the two values of 0 and 1 for x. These two equations may be rewritten as this matrix equation, and this is what it is after we evaluate all of its elements. And so we make the coefficients of the line into the subject of this equation, and then we can very easily calculate the inverse of this matrix. Then we have to calculate the area of this shaded segment, which is equal to this integral. And then this integral may be rewritten this way, using the line's antiderivative. And so these two numbers are substituted in for x. And so this is the expression in its most simplified form. And then this expression may be rewritten as this vector equation. And so now we have these two matrix equations, and we have to use these to find the area of the segment in terms of the heights of the function, y0 and y1. And so we substitute 1 into 2 to give this expression, which is independent of the coefficients of the line. And so after multiplying this vector and matrix together, this gives us the trapezoidal rule for an interval of 1. To get the trapezoidal rule coefficients for a large number of points, we'll use the example here of a curve being approximated by these trapezoids. We'll calculate the shaded area under the curve by adding all of these trapezoidal areas as shown. And since some of the y's are found twice in the calculations, then they are added together to make this sequence. So the y's in the middle have a coefficient of 1, and the y's at the ends have a coefficient of 1/2. We can use any two numbers separated by 1 for x to derive this rule using this method. Here we're using -1 and 0. And we can rewrite these last two equations as this one matrix equation. And evaluating the elements of this matrix gives us this matrix. And so now we're calculating the coefficients in terms of the heights. And inverting this matrix gives us this matrix. And now to calculate the shaded area under this line using this integral. And the next step is to calculate the antiderivative. And then the next step is to substitute all of the values in for x. And then we expand and simplify this expression. And then we have this expression in its most simplified form. And then this expression may be rewritten as this vector equation. And so now we have these two matrix equations that we must use to derive the trapezoidal rule from. And substituting 1 into 2 gives us this expression, where the area is given only in terms of the y's of the function. And simplifying this expression gives us this vector equation, which is the trapezoidal rule for a single trapezoidal segment. And we can use the expressions n and n plus 1 to derive the trapezoidal rule. We firstly convert these two equations into this one matrix equation, and then we evaluate the expressions containing n. And so then we express the coefficients of the line in terms of the heights of the line. And so getting the inverse of this matrix gives us this matrix, which can be done using a special program that can find the inverse of a matrix containing one variable. It is more complicated than the previous two, since the matrix contains a variable, making it harder for the computer to work with than a matrix containing only numbers. And so here we calculate the area of this shaded segment, which is equal to this integral. We can then write down this part which contains the antiderivative of this line function. Then we can substitute the expressions n and n plus 1 in for x. Then we can expand all of these expressions. And then we get this answer in its most simplified form. And so it can be rewritten in this vector form. So now we have these two matrix equations, and we have to use them to derive the trapezoidal rule. We then substitute equation 1 into 2 to give us this equation, which doesn't contain the coefficients of the line function. And so simplifying this equation gives us this, which is the trapezoidal rule for a single trapezoidal segment with a width of 1. And now to derive the trapezoidal rule for the more general case of any two points that are a distance of h apart. We rewrite these equations as matrix equations and manipulate them so as to make the coefficients the subjects of these equations. We finally have to find the inverse of a matrix with two variables, which is much harder than finding it for a matrix with only one variable. The fact that it is only a 2 by 2 matrix makes it doable. Now to find the area of this very thin trapezoid using this integral. It is quite a messy calculation, but in the end we get this vector equation. So now we have these two matrix equations to find the trapezoidal rule for any two numbers n and h, and it gives it to us with this variable h in front. And so now to derive the trapezoidal rule using samples of trapezoidal straight line functions. We know that the solution is going to be linear, and there are only two coefficients to find. So we only need two groups of data from two straight line functions, and two values of x, 1 unit apart. But we've got to include these two values of x in both groups of data once they have been chosen. We want to get equations of the form shown, where the two different y's or heights of the function are shown, with a single number representing the area under the line, on the left-hand side of the equation. The values of b will be the coefficients of the trapezoidal rule. So for this function and values of x, these are the values of y. And to get the shaded area under this line, we need to evaluate this integral. And after getting the antiderivative of this function, we get this next line in the derivation. And we get this line after substituting the values in for x. And so we get this value for the shaded area under the line. And we can write out this vector equation to solve for b, which are the coefficients of the trapezoidal rule. And because we need two sets of data, we'll use this equation to find the second set of data. And so these are the heights of the function using the same values of x as we used before. And we'll evaluate the shaded area under the line using this integral. And calculating the antiderivative gives us this. And substituting the values in for x gives us this, which gives us this amount for the shaded area calculated as a number. And so we can write out this vector equation to describe this second set of data. So now we have these two vector equations which we need to calculate the trapezoidal rule from. And so we can pack them up into this matrix equation. Solving this equation will give us a solution to both of these vector equations written on top, and thus give us the coefficients for the trapezoidal rule. And so to solve them quickly using linear algebra, we get this solution, which are the coefficients of the trapezoidal rule. So I hope that this has been helpful for you to get more used to using these methods so that you may calculate the areas under the curve using polynomials that are very large, like with degree 10 or larger. Thanks for watching.